walks and various aspects of quantum walks.
Thank you very much. Before I start with my seminar, I would like to show you the map of my scientific interests, which evolved in time. As you know, I graduated with Professor Lutkiewicz at Boson Physics Department in quantum mechanics, with a little bit twist to nonlinear phenomena. My habilitation thesis was devoted to macroscopic quantum phenomena, as the size of the systems I was interested in was getting larger. And these three topics are the topics which I started after I finished my habilitation work. I started working on them this year. This topic, complex systems, is related directly with quantum walks, and I will present it today. And the other two topics are condensed matter. This is related to polaratomic Bose-Einstein condensate and quantum thermodynamics. This is the most recent scientific interest of mine. Quantum walks, mastering the complexity and the uncomputable. This is the outline of my talk. It consists of 4 parts. The first part is devoted to motivation. I would like to show you the class of problems which we encounter in science, not only in physics or chemistry, but the whole science, including social sciences, where using traditional methods we are helpless. These problems are simply intractable or very, very difficult to obtain any insight. The second part is devoted to review on quantum walks. These are just basic definitions so that we were all on the same page. Part 3 is devoted to examples presented in the most recent literature where quantum walks were successful in describing or explaining certain phenomena in complex systems. And part 4 is devoted to one particular example, the quantum leap, and this is my modest contribution to this field. This is the map of physics. Classical physics, quantum mechanics, relativistic quantum mechanics. Wherever we are, we always do the same. We seek for a Hamiltonian, and we are trying to solve equations of motions. How far we get with this approach? If we had a complete solution, we would have dynamics of the system for the past, the present, and the future. But in practice, most often, we are only interested in dynamics taking place in certain interesting interval of time. Thus, we don't need these solutions. There are only very few systems which are exactly solvable analytically. And these comprise harmonic oscillator, periodic particle in periodic potential, hydrogen atom. If we can't proceed analytically, it is natural to think that perhaps we can use computers to solve our equations. But it soon turns out that even big computer clusters are also helpless and can't solve these equations for the interesting regimes of parameters. Let's take a closer look on the issue of computational complexity. This is the map of most frequently discussed computational complexity classes by physicists. It comprises 2 disjoint sets. The bigger one, this is the set of complexity classes related to decision problems. The decision problems are those where we want to compute a function, how much certain function of parameters is. The most known class is the class P, because this class comprises all the problems which are efficiently solvable with classical computer. Thus, any actually computer we have at hand. The class BQP, this is the direct generalization of the class P for quantum computer. Thus, it comprises problems which are efficiently solvable by quantum computer. Class NP, which includes class P, this is the class of problems which are efficiently checkable on classical computer. Thus, if we have already a solution, verifying that it indeed fulfills equations is easy. This is the set of problems. QMA class, this is the direct generalization generalization of the NP class for quantum computer. Problems efficiently checkable on quantum computer. The other class of problems, these are the function problems, and here the most often discussed class is the HP or its generalization HP complete problems. This is the set of counting problems associated with decision problems in the set NP. In short, we in this class are interested in counting how many solutions to certain problem there are. Please note that although a problem formulated as a decision problem itself can be very simple and belong to class P, counting how many solutions there are might be very difficult, and then this problem, formulated as a function problem, belongs to the class hash P. These are examples of classes of problems we encounter in science. Complex networks. For example, the traveling salesman. We map the evolution of a problem on a graph, and we are seeking certain path in the graph, fulfilling a condition, the shortest path, the most known path. This problem belongs to NP complete class. Thus, it's at least as hard as NP.
Sorry. So we do not have any algorithm to check whether a given solution is the optimal.
There are algorithms, but they are very, very
so not efficient.
Not efficient. Complex interacting many-body systems. For example, in quantum chemistry, we are seeking for ground state wave function of interacting electrons in complex molecules. This is the quantum Merlin-Arthur class of problems. Quantum interference, multi-particle, many-node. For example, the Boson Sampling problem. This is the class HP complete. Basically, these problems are intractable with any classical computer.
Well, it looks beautiful, but if you could tell, because I don't know what is Boson Sampling.
I will talk in detail in further slides.
Pictures are beautiful, but it would be nice.
I would have another remark. In this range of problems in quantum chemistry, there are various levels of approximation.
Yes.
And at these various levels, of course, we can compute things, and in most cases, this is absolutely sufficient. So this notion of solubility is kind of not very well suited for physical problems.
I will agree.
Almost everything that we are doing is approximate anyway.
Yes, but there are these density functional problems and computations which are, for example, their accuracy is plus minus 100% or something similar. Thus,
yes, but all these mathematical theorems that you would be perhaps somehow referring to or you have in mind, they do not apply with maybe slightly better approximation. They really apply to the exact Hamiltonian, and even this exact Hamiltonian is not exact because it's always some involvement and there's some interaction of something.
And
So placing this in some class is kind of not really very physical.
And the quantum chemistry is particularly unpleasant example of the computational problems. For
yes.
after all, you can go to the pharmacy and buy the hundreds of products which don't kill people, which have been computed by quantum chemistry.
Yes.
And in some cases they even help. Not often.
I understand that this is an introduction and that's why.
Yeah, but there are so many
No,
pictures.
but just placing this in the form of categories and so on, it's misleading at least as far as physical problems go. Because physical problems are always approximate and there are always computable methods of doing something with some accuracy and then maybe improving this accuracy just a little bit.
I'm not sure if this is what these authors of this publication claim. Of course,
I know what I claim.
Of course, every problem has an approximation. However, there is whole theory of how accurate and how complex these accurate approximations are in computational complexity. And this is always a question, how far we want to go. So, thus a natural question comes, perhaps a quantum computer would help in solving these difficult problems. And the answer is no. According to the current state of our knowledge. The hypothesis is that the class BQP is roughly equal to class P. Thus, the famous question whether class P equals to class NP has a rather negative answer. And why this is so? Because quantum computer in fact also solves equations of motions. And it is proven that every function computable by a quantum computer is also computable, if more slowly, by a standard quantum Turing universal machine. Actually, there has been found only one only one significant example where a quantum computer can perform a classical computer, the prime factorization, the Shor algorithm. But it's important to remember that actually there is no proof that its classical efficient counterpart doesn't exist. No one knows. Perhaps it's just not found yet. And here, I hope this explains the motivation for quantum walks. They offer completely different approach to solving problems. They offer algorithmic approach, which is explained in this frame here. This is divide the complex long evolution into many small easy steps. Instead of seeking complex Hamiltonian, which generates complex long evolution, apply simple local unitary transformation for short time, many times. This is mathematically justified by the so-called Trotter-Suzuki formula, which says that if the time step is sufficiently small and we will iterate our procedure sufficiently number of times, we will find our complex evolution exactly. We will restore our complex evolution very exactly. This is illustrated.
I don't understand this stress on algorithmic approach. Everything we do is algorithmic approach because there is some rule which can be called an algorithm. So why do you connect algorithmic with quantum walks? It's just a different.
Any calculation seems to be algorithmic.
It's algorithmic in this sense that it resembles how things are treated in computers. These operations can be sort of understood as applying gates.
That applies to anything that is on a computer. That is nothing specific about quantum walks. Even solving quadratic equation is an algorithmic approach. There's a rule how to proceed.
I see what you mean. So here, in here, I meant that it's applying certain operations, certain gates. This is what I meant.
So this is, we always do this with the computer. Why? Quantum walks are special in this respect. If one solves ordinary differential equation, it's the same rule. Because computers don't handle continuous functions.
Yes.
So I'm trying to understand why quantum walks are here treated on a different footing, that there is something special as compared to other methods.
Yes. So in the literature, what I understood by this, they mean that they are applying certain amount of operations which are just gates, like building blocks. Of course, I understand that every computation is done through algorithmic approach and writing the set of rules and how we move on the graph, how we choose the vertex in a graph and what rules we apply. I understand what you mean, but here it seems that in community, algorithmic approach is understood as applying black boxes, like small building block operations, which are repeated many times.
The Trotter formula has been applied for many, many years.
Yes, I know.
And it has never been called quantum walks. If what you mean is Trotter formula, then why should this be called quantum walks?
Yeah, that seems to be a semantic problem. Let's proceed.
This picture illustrates what I had in mind by these claims here. Instead of considering complex evolution of whole big system at once, we are decomposing this evolution into simple evolutions, for example, involving only next neighbor interactions, and we repeat this many times. This is the key idea behind simulations, in particular quantum simulations. And there are mathematical proofs that this kind of approach is most optimal. Thus, that simulation complex systems, dynamics is more optimal than solving equations of motions. This approach is more optimal than solving equations.
This also applies to classical
Yes.
evolution.
Yes. Yeah, absolutely.
Just a finite
Yes. Yes.
step.
Yes. Yes. Quantum walks are generalization of random walk. Random walk is a path consisting of a sequence of random steps taken according to some probability distribution. For example, a cat wants to move forward and take a step left or right. Thus, it tosses a coin. Each time it wants to take a step, it tosses the coin. If this is performed sufficiently number of times, the position of the cat, the final positions of the cat in the graph, according to the central limit theorem, follow the binomial distribution, which variance scales linearly with time. Here, time is equal to number of steps. One-dimensional random walks are Markov chains, and Wiener process describing the Brownian motion is the scaling limit of random walk. Now, the quantum walk, the cat, is now replaced by the Schrödinger cat, which can exist in quantum superposition. Thus, it is governed by a unitary evolution, which generates superposition, but which is deterministic. No randomness is involved here. And for this reason, we are encountering a problem, a single-step problem, because a unitary evolution in this way cannot make the cat to take steps simultaneously left and right. We can solve this problem in two ways. Let the walker spread over all positions in the graph in a single step. Or introduce another degree of freedom called the coin degree of freedom, for example, implemented by polarization. This degree of freedom will mimic the randomness as it was in classical process. The second model corresponds to the discrete-time quantum walk. And here, a step of a walker consists of two operations, tossing a coin and conditional shift. Most often chosen coin is the Hadamard coin, which has this particular feature that it does not treat in the same way the head and tail, not in equivalent way. Thus, it may happen that we end up in a non-symmetric distribution, but by choosing cleverly the initial coin degree of freedom for the walker, we restore the symmetric distribution. These two pictures show the probability distribution of final positions of the walker in the one-dimensional graph after 100 steps, providing that the walker started in the middle of the line. Importantly, these distributions are double peak shape or U-shape, not binomial ones, and their variance scales quadratically with time, thus quadratically faster than in the classical case. This is the distinguishing feature of quantum walks with respect to classical walks and the cause for potential quantum speedups and advantages. The other model, where we let the walker to spread over the whole graph, corresponds to continuous time quantum walk. Here, the evolution takes place only in the position Hilbert space, as shown in this graph here, and the Hamiltonian sets the amplitudes of hopping between one and another vertices. In this way, in this spirit, continuous time quantum walk is similar to quantum cellular automata because these set the transition equations. This graph shows the probability distribution obtained in the continuous time quantum walk for the same time, t equal 100, providing also that the walker started in the middle of the line. Although this distribution exact shape is a little bit different, the common feature is that it also is characterized by the ballistic spread. Surprisingly, and a little bit weird feature of this model is that the walker can be transferred arbitrarily far from the starting position. To summarize a little bit, we are dealing with quantum walks most often. We are dealing with quantum walks in two flavors.
Excuse me, what do you mean by this statement that the walker can be displaced arbitrarily far? That also happens in the normal classical random walk, because in the limit it's a diffusion equation, and the diffusion equation
Yes.
Parabolic
Yes.
equation,
Yes.
so it is a property of a
Yeah.
parabolic equation, no?
Yes, I agree.
So there is nothing peculiar. So how come that comes here?
It's simple fact.
I always thought that the Schrödinger equation is not parabolic.
It's the simple fact that this amplitude, this transition amplitude, set the probability of certain events. Thus, it may happen that the Hamiltonian is not really local, and due to some strong correlation in the system, it may happen that Hamiltonian will connect vertices which are very distant.
Well, anyway, there is a statement which has nothing to do with this. The statement that Walker can be transferred, I mean, I'm reading the statement. Walker can be transferred arbitrarily far from the
That
starting
means-
position. That's the property of a parabolic equation.
Yes.
And also
Also the
Schrödinger
Schrödinger
equation,
equation.
which is not parabolic, but still the velocity of signal may be.
Yeah.
It's almost parabolic.
Yeah.
So there is nothing.
Okay.
In a sense, it looks also like a hyperbolic.
Yeah.
It does not fit into this classification.
We are dealing most often with two flavors of quantum walks: the discrete time, where the time and space is discrete, and continuous time, where time is continuous and the space is still discrete. This is an important remark, because discrete space means that we can actually map the evolution of our system on a graph, and thus it's easy to represent in computers. There is important assumption behind this, because that we can describe the evolution of a system accurately in a countable basis of states. This not necessarily is so. Quantum walks turn to random walks in presence of decoherence, or if the position of a walker in the graph is measured after every step. Relation between discrete and continuous time quantum walk is complex, and here I'm briefly summarizing the case for one-dimensional walks. Namely, it is possible to turn one-dimensional continuous quantum walk, the transition equation, to Schrödinger equation, describing non-relativistic free.
Could you possibly decipher those abbreviations, because
Discrete time quantum walk, continuous
oh.
time quantum walk. Whereas the discrete time quantum walk corresponds to Dirac equation describing relativistic free particle.
In one dimension.
In one dimension, yes. Therefore, discrete time quantum walk limits to the continuous time quantum walk in the limit of very heavy particle mass, which is corresponding to appropriate coin bias. Generalizations are possible to arbitrary dimension, arbitrary coin operations, multiple walkers, arbitrary graphs. And I will not go into further details, which are very nicely described in these two reviews. I will now present the puzzles we have in this research. Namely, I said that the quantum walk is different from classical walk in the sense that it spreads quadratically faster. But is this really the defining feature? It has been shown that discrete time quantum walk on a line can be simulated by classical systems, for example, classical electromagnetic wave interference. Also, that quantum walk with inhomogeneous time-dependent coins simulates a random walk. We have Gaussian statistics accompanied by very high coherence. Thus, how do we know that the evolution underlying a walk, quantum walk, is quantum or classical? This is important. If I receive only statistics and say it's U-shaped, it has potential to be quantum, but how do I know that it's really quantum? Because if it's only mimicking, I will not be able to use this process for some quantum information protocols or quantum protocols which rely on quantum advantage, quantum speedup. The current hypothesis following the state of art is that the evolution underlying quantum walks is quantum if it involves interference of many indistinguishable particles, Hong-Ou-Mandel interference with interferometric contrast of quantum value, or it leads to violation of some classical inequality. And this sets the current direction in research on quantum walks. Quantum walks have been successfully implemented due to advances in integrated optics, and where we distinguish two basic setups: optical waveguide lattices and coupled waveguide arrays. Here, in optical waveguide lattices, the channels in the waveguide are so close to each other that the photon actually tunnels, hops between them. In optical waveguide arrays, the interference is enabled by so-called directional couplers. The two waveguides are brought together, and here the photons interfere. 2- and 3-dimensional structure have been demonstrated. Quantum walks have been also implemented with condensed matter systems, and in particular, the most interesting one, from my point of view, is the demonstration using rubidium atoms in optical lattices. They were prepared in the mode insulating phase. And the work has been shown for, investigated for weakly interacting bosons and strongly interacting bosons in fermionized regime. This is the only demonstration of quantum walk where the particles are interacting particles. Now I would like to discuss the various phenomena where quantum walks have been useful in description or explanation. One of the most important phenomena encountered in complex systems is the Anderson localization. It turns out that the quantum transport in disordered media, where the disorders of static or dynamic character can be completely stopped, and localization of a wave function is observed. This happens as a result of destructive interference between different scattering paths. This phenomenon has been simulated in integrated optics by the setup shown here. The disorder was at first statically and then dynamically implemented, and was position dependent, namely a certain delay between the neighboring waveguides was introduced, and it was regulating the length of optical path. Two entangled photons were used in order to investigate this effect for bosons and fermions independently. The following results has been obtained. On this picture, I'm showing the quantum walk, which is a usual quantum walk without any disorder. We see that for bosons and fermions and single particle, the wave function spreads quadratically without any disturbance.
So what are these bosons here?
This is the singlet state. Excuse me, this is the triplet state of two photons, entangled two photons, a pair of two entangled photons. And fermions, this is the singlet state. Then the probability distributions for bosons, fermions in presence of static and dynamic disorder was measured, and we see the effect of localization.
Maybe I get lost.
Yes.
What are the axes on these beautiful pictures?
This is the position.
On
Two-dimensional.
the lattice or what?
On the lattice, yes. On the lattice.
So the points are the cells or the nodes or what?
Oh, the vertices are in the lattice. Yes. It's a
So the size of these blocks is irrelevant.
yes.
They could have been points.
Could have been points.
But for what were the fermions used in this?
Singlet state.
Of two photons
Singlet
again.
state. This
So
group,
these fermions were bosons.
Antysymetryzowany stan.
In what sense these are fermions?
the statistics. This group has shown that by simulating, by adjusting the phase between two components of product state of two photons, so for example HV, VH, by introducing the plus or minus phase, they can simulate bosonic or fermionic
So-
statistics.
These are fermions in a sense like a Cooper pairs. You have a bound state of
I would guess this is what they have.
the other way, the
Yes.
Cooper pairs.
Yes,
Cooper
yes,
pairs. You have a
yes.
boson built up from two fermions.
I think so. If any interaction was involved, probably this would already be different. Another class of problems where quantum works were useful is description of artificial Gaussian fields. They are useful in modeling electrons on two-dimensional lattice in magnetic fields. And here we encounter such problems as quantum Hall effect if they are weakly interacting, or new states of matter if they interact strongly. This Hamiltonian have been chosen to simulate artificial magnetic field, which is encoded as phase shifts during the evolution on a two-dimensional lattice.
Why it is artificial?
Because there is no magnetic field.
Because these are not gauge fields.
Yeah.
Yeah, but I mean, if I had a two-dimension lattice, and if I put up in the lattice something which I can do experimentally, which in that sense is never artificial, an array of a Bohm-Harrer of wires, the fluxes, the Hamiltonian for electron propagating in that construction is exactly as what you want. So
I
it's
agree.
not artificial. I mean, I can build the device.
Łukasz, these experiments are done with neutral particles, with bosons typically, or fermions sometimes. So they are not
Yeah, well,
sensitive to
I
the
was just
magnetic field.
talking about the electrons.
No,
It's
no,
written
she's not-
modeling, well, okay.
No, she's not talking
In
about-
any case, this kind of Hamiltonian is perfectly
Yeah.
experimentally constructed.
Yes.
Yes.
In that
Yes.
sense, it's not artificial.
It is artificial because there is no magnetic field.
Because there's no real gauge field
Yeah.
there.
There is.
That's
Gauge
what.
field.
No.
Magnetic field.
No, there is no magnetic field.
No.
If you do
Well,
it,
I'm
use a lattice.
saying that I can make the Hamiltonian
Yes, you can.
like this by using a completely
Yes, you
physical
can.
field.
Yes.
And they also,
Which is
and
gauge.
that's why this is artificial, because they do it other way around, without
Yes,
this field.
without field. And yet the effect is the same phase factors.
Yes, so now, instead of, as Professor Tursky said, instead of using real electrons in real two-dimensional lattice and applying magnetic field, we are using again photons which propagate over two-dimensional graph, and they are exposed to certain phase shifts in every vertex-dependent phase shift. They don't experience any magnetic field. This Hamiltonian describes accumulation of phase if we consider transition over loops in the two-dimensional lattices, two-dimensional graphs. It is possible to map this complex Hamiltonian onto a quantum Hooke Hamiltonian in the following way. We decompose it into a sum of 4 Hamiltonians, each implementing a beam splitter. 2 of them are implementing a usual beam splitter, symmetric beam splitter, and the other 2 are implementing a beam splitter which introduces a phase shift, phase-dependent beam splitter. In this way, this model can be simulated on a 3-dimensional array of beam splitters and phase shifters. Here, this is the picture of how the phase shifts have been implemented, and we can observe and compare these 2 pictures, what phase shift, which operation is applied on certain node. In this model, it was possible to restore the energy spectrum in the form of Hofstetter butterfly, typical to two-dimensional electrons in strong magnetic fields. Yet another interesting observation has been made that quantum transport in presence of disorder and simultaneously magnetic field is enhanced over the ideal case, assuming perfect coherence, no losses, no decoherence, we will obtain a better transport efficiency if we introduce disorder and magnetic field. And this is illustrated by this picture here. This line corresponds to the ideal situation, perfect coherence, and the other two curves correspond to introducing phase shift, disorder and magnetic field. The boson sampling problem. It came as a big surprise to the community roughly 4 years ago that linear interferometers can lead to extreme computational complexity. We can consider the most simple case, namely interferometer like the one here. We have m input modes, m say 100, and only n out of them are seeded with single photon, and n is small compared to m, so say 10. 10 photons, 100 input modes. We let them interfere, for example, through the Hong-Ou-Mandel effect. The outcoming superposition is intractable, completely intractable if the number of modes is roughly 30. Why this is so? It's because number of configurations in which these 10 photons can appear on the output is super exponential, proportional to this binomial. But also because every single amplitude, probability amplitude here, computing it, is actually equivalent to computing a permanent of a very, very large matrix. This is a super cumbersome problem requiring super exponential computing time.
So this very huge matrix is just of the order 100, yes?
Permanent, yes.
Yes.
Permanent, for example, yes. Mm-hmm. But computing
So
already...
of your notation m.
Yes, but yes.
So it's worth stressing that the same size determinant is no problem, but the permanent is indeed much harder.
Yes. And what struck me in person is that boson sampling does not let us calculating this matrix permanence, only sample them. And what does this mean? In the laboratory, we are capable of producing an output state which is completely disconnected in any informational sense from us. We will be never able to learn about it. We can produce something which we cannot compute, cannot measure, cannot do anything. We only sample them. Because sampling means that even if we measure the output here many, many times, this data which we collect does not let us restoring statistics. We cannot have any mean value, we have no moments.
I will ask why we cannot have moments. If we do it many times, we have statistics.
No, because there are so many of them that you basically in practice receive certain output only once. So you just never repeat it. It has been shown that actually similar complexity arises in the standard implementation of quantum works if we consider instead of single photons or 2 photons, more photons. For example, we will introduce 9 photons here and 9 photons here, and we will take 16 steps. The number of configurations which will appear here exceeds the number of atoms in the universe. Thus, the general conclusion from this works is that the difficulty arises from 2 effects. Hong-Ou-Mandel effect, which creates exponentially large Hilbert space in number path, and the fact that at the end we are brought to computing the permanent of a very large matrix with complex entries. Another interesting example are the topological phases, and quantum phases of matter have been shown to be linked to the non-trivial topology of Hilbert space of our system. For example, the Chern numbers allow us to observe integer quantum Hall effect. Chern numbers are closely related to the Berry phase, thus to the parallel transport on a sphere. We know that if we let the vector to be transported along the closed loop, the vector which we will obtain at the end is not parallel to the initial vector. The difference between them is proportional to the solid angle behind this loop here, and this in turn is related to the Chern numbers. This kind of effect can be observed for two-dimensional electrons with strong magnetic fields. Their ground state wave function is related, numbered by these Chern numbers.
And also can be observed in the steps on the staircase. In the concrete steps on the staircase when it breaks, because this kind of fancy phenomenon is nothing else than the Frank angle in the solid states theory. So it's known since probably hundreds of years.
Yes. I absolutely agree. Topological phases in the form of quantum, in the form of Chern numbers have been observed in two-dimensional walk of spin 1/2 particle on square lattice. This is the quantum walk which simulates them. We have a walker localized in the middle of the graph. We let it rotate, then we take a shift, we rotate again, we take shift up, shift down, we rotate again, take shift left and right. In this way, this unitary transformation implements effectively the following Hamiltonian. And the whole mystery of this non-trivial topology is hiding in this vector n, which is the quantization axis for momentum k. In this way, this vector n maps the first Brillouin zone in the form of the torus to the block sphere. Small piece is mapped onto a small piece. But if we want to map the whole torus, it will turn out that we will warp the sphere few integer number of times. This integer number of times corresponds to the Chern number. And in this way, energy spectrum of topological insulator has been restored with the exhibiting the gapless edge states. Quantum walks have been also shown to efficiently describe quantum maze, classically intractable. However, quantum walk can more efficiently reach the output of a maze by partially suppressing quantum interference, namely by adding controlled number of decoherence. This setup has been mapped onto an array of waveguides in the following way. The walls have been simulated by coupling between the waveguides and thus the distance between them. In order to keep the walker in the output, not to let it go out again, a sink in the form of chain of waveguides has been designed. Here, the graph shows the efficiency of transport between the input and the output as a function of the size of the maze in presence of controlled amount of decoherence. These are the blue dots, perfect quantum case, the black triangles, and red squares, classical walk. We see that that the effect is larger for larger mazes, and here they have obtained increase in the efficiency of transport 5 orders magnitudes with compared to the classical, and I think 3 orders of magnitudes with respect to the purely quantum case. Now I would like to proceed with part 4. This is my work, which I have prepared together with my friends Peter Rodi and Paweł Burzyński in discussion with Professor Zeilinger. The concept we are discussing is the quantum leap. And the question we have asked is the following. Are there genuinely quantum processes which can accelerate quantum walks evolution and which can be achieved with fewer or complementary resources? Why did we ask this question? As you see, implementation of quantum walks requires huge number of elements, optical elements and also detectors. Graph of size O of n requires n-squared beam splitters and detectors to take n steps, or n-couple waveguides, also n detectors to implement n positions. That means this is very, very difficult to simulate a long quantum walk. And also, it's difficult to eliminate side processes which can happen during the evolution and which will eventually lead to phenomenon similar to Anderson localization. If we want to take a long evolution, we would rather make it in one step, in one leap, and this was the idea behind the concept. Thus, quantum leap is a process which in a single step simulates another long process. The idea is that the original Hamiltonian of the process is preserved, only the evolution takes place not in the physical time, but along a parameter, adjustable parameter of a setup. In this way, for quantum walks, quantum leap will immediately give a probability distribution which would be obtained only after long evolution. And in this way, this is appealing approach for simulation of processes which require long evolution or involve dynamic control, because then dynamics can be performed within the space of parameters. The example we are examining is based on Hong-Ou-Mandel. Thus, this is the Hong-Ou-Mandel quantum leap. Our system parameter is set by the reflectivity of beam splitters. So instead of considering evolution in time, we will consider evolution in this parameter. We consider interference of n photons from the right and n photons from the left, and we are examining the occupation in the output modes. I will show you that.
Excuse me,
yes.
I'm afraid that very few people here in the audience ever heard of Hong-Ou-Mandel.
Next
You are
slide.
using this, well, you are using this notion not for the first time here, as if was known
Next
to everyone.
slide is clarifying. Next slide. Okay, so maybe I will choose. I will come back to this slide. So Hong-Ou-Mandel interference is implemented by the beam splitter Hamiltonian, which in case of a single photon sends the photon randomly to the left output port or to the right output port. Single Hong-Ou-Mandel effect has been originally observed for interference of two identical photons. So two identical photons enter the beam splitter. And due to the bosonic character of this interference, the two photons will always exit together. They will bunch. They will never go apart. And this effect can be generalized to interference of many photons. It turns out that if we will consider, instead of single photon here and single photon here, many photons here, but fixed number, say 10, and fixed number here, say 20, they will also exit in certain configurations. So some configurations are allowed and some are completely separate.
But the exact matching of the wave packets is still required, yes.
Yes, absolutely. In all degrees of
So
freedom,
it's
they
not
have
possible
to
to
be.
do experimentally, at least not now.
This Hong-Ou-Mandel interference, this is a very active area of research, and
Yes.
they are examining it for various systems. I will also show this a little bit. So to finish what I was going to say about this slide, I am considering this system, and I will show that this simple system, although it involves only single beam splitter and two Fock states, it can mimic a specific continuous time quantum walk on the line with S+1 vertices. S is the total number of photons entering this setup. And importantly, I am omitting the problem of the question whether it's quantum or classical. We know that the Hong-Ou-Mandel interference is inherently quantum phenomenon if its interference contrast exceeds the value 1/2. Thus, I can easily measure the contrast. This is something one can easily do. I measure contrast and I know. Okay, just to finish this slide, multi-photon interference, of course, multi-photon Hong-Ou-Mandel effect is being considered for increasing number of photons in the original setup, as well as increasing the number of input ports, thus replacing a beam splitter 2-port interferometer by M-port interferometer. As I said, Hong-Ou-Mandel interference for two interfering Fock states can be inherently quantum process, and these graphs show for which configurations between two fixed number of photons I am achieving purely quantum contrast, and I have the problem set. A quick reminder from the continuous time quantum walk. It takes place on a graph, and the Hamiltonian sets the amplitude for the particle hopping from one vertex to another. I am starting with the well-defined position in the graph, in the initial moment, and after some time I should obtain statistics of the outcomes, and the statistics should follow ballistic spread. Okay. As I said, quantum leap mimics some process, thus the original Hamiltonian is preserved. So this is the original process which leap will replace. So the original process is Hong-Ou-Mandel continuous time quantum walk. Thus quantum walk, which is generated by the Hamiltonian of beam splitter. The two interfering Fock states can be actually described by occupation difference between them. Thus, I am assigning that such two Fock states are actually modeling one particular vertex in the graph. Behind the beam splitter, the infinitesimal evolution turns the Walker position to the following superposition. One step to the left and one step to the right. I can show that actually the number of positions we can have here is S plus 1. S is the total number of photons. Total number of photons in the system. Now, simple algebra shows what is the structure of these hopping amplitudes. And it turns out that they exactly follow the jump amplitudes characterizing important class of quantum walks, those which allow perfect straight transfer over arbitrary long spin chains. Thus, I have an arbitrarily long spin chain, and its length in my model I am setting by taking enough amount of photons for the interference, and I can perfectly send over the spin chain quantum state. This is easy to understand why this is so, because the Hamiltonian of beam splitter is in fact the spin Sx operator in the Schwinger representation, and two Fock states mimicking the position in the graph can be understood as a fictitious particle of total spin S over 2 and eigenvalue of the Z component delta over 2, thus this initial difference. Hong-Ou-Mandel interference rotates the SZ component.
These A and B in your original Hamiltonian are just creation annihilation
Yes.
operators of bosons.
Yes.
So we have that. I don't understand how do you get a spin which has finite number of states, whereas the harmonic oscillator has infinite.
But my number of photons is fixed.
So what?
Energy is fixed in the system.
Yeah, but the Hamiltonian is quadratic, so it's exactly soluble anyway.
Yes, but I'm just showing that this system can mimic some other process. I'm not saying that it's not solvable. I'm not saying that.
But it is solvable.
Of course, yes. I am only showing, what I am showing actually is that this relatively conceptual system can simulate a transfer of perfect transfer over spin chain, completely different process. Completely different. I'm just showing that this system simulates another system. I'm not saying that it's not solvable. I'm just...
So you are considering now this Hamiltonian in a restricted Hilbert space?
Yes.
Okay, if you can construct out of Boson creation and annihilation
Yeah, sure.
operators, for example, operators which fulfill spin.
Of course, for
spin.
anything.
Yes, and then this if you construct in some Schwinger construction, whatever it's called, and it then produces arbitrary representation of the spin. But if you start with some in some representation, and the Hamiltonian will keep this constant of the motion, so it will stay in the finite dimensional Hilbert space.
Okay.
Now, I am considering quantum leap. So this leap simulates the other quantum walk. The Hamiltonian is still the same, but the evolution is taken in the space of parameter, the reflectivity of beam splitter. This angle theta is related to reflectivity in the following way. If the reflectivity equals 1, a well-defined initial vertex in the graph is mapped to its opposite vertex. If r equals 0, we observe a certain recurrence in quantum walk. For all other values, we obtain the probability distribution of final positions characterized by the following variance. Scaling quadratically with the evolution parameter. Importantly, whatever non-zero number of particles we are considering in the system, and whatever the occupation difference is, the spread is always ballistic. And by setting S and delta properly, we can simulate an arbitrary advanced stage of evolution. These are the pictures which I obtained for my system. Correspond to the colors correspond to the following values: green 1/10, red 2/10, blue 1/2. We see how this distribution obtained behind the beam splitter spreads. If we set properly the reflectivity of beam splitter. These three graphs correspond to various initial population difference. Here, two identical Fock states interfere. Here, two non-identical, but none of them is 0. And here we consider interference of a Fock state with the vacuum. And this case exactly corresponds to the perfect state transfer. We see that this green distribution is reflected by the gray distribution. This model is robust to losses. Of course, the probability distribution are a little bit distorted, but we never lose quantumness because Hong-Ou-Mandel interference visibility is immune to losses. This is important. And this simulation has been performed for Fock states of purity roughly 1/2. And we can observe the quantum to classical transition. Probably you recall that the quantum walks turn into random walks in presence of decoherence. In this model, it is simulated by introducing polarization degree of freedom. Now, two interfering Fock states do not have the same polarization. One of them has a little bit rotated. How much? Sets the degree of coherence in the system. This picture corresponds to distinguishable photons, and then we are slowly indistinguishable, and then we are slowly increasing distinguishability. Here, they are completely distinguishable. Thus, we restore the classical dynamics.
So this is no longer a Hamiltonian evolution.
It is Hamiltonian. We model.
How do you introduce losses in a Hamiltonian?
Losses are not really particle losses in this model. It's in.
But in the previous case, you had losses. You said.
Yes, I had losses. That
So
means.
How do you obtain losses in the Hamiltonian description?
I do not obtain them in the Hamiltonian description. I take different input state.
So what?
Mixture of Fock states. mixture of Fock states.
What is the evolution then? It's governed by the Hamiltonian?
Yes, yes, yes. It's
So
still,
it's not, have no losses if it's unitary.
no.
Unless loss means something else.
No, losses usually
Usually.
meaning that.
Or it could be such a situation.
Not unitary.
Okay. I am considering losses in two different ways. At first, imperfect preparation of Fock states, because this is difficult.
But this is still, but if the evolution is unitary, then I would not call it losses.
Yeah, this is not loss.
So that's what I said.
Okay.
Where losses is not
Provided that you
reduced.
do not
Well,
reduce
why
to
not
some
just
subsystem.
Okay, I agree.
In
And
this
then-
building,
Yes,
in the
I
school
agree.
edifice, the words are used,
Then,
not usually in the normal sense.
first thing, okay, maybe that was the problem with wording. I am considering imperfections. First, important is that Fock states are not really pure, nice Fock states.
So you
That's
mean
one thing.
density matrix?
Yes.
What is the evolution
Another.
of the density matrix?
Another, the same. Here is the same, because it's just no loss. No
Yeah,
loss.
okay.
In another model, and I think this is, I think I am not showing this in this presentation. Another model which I am considering is lossy detector. Thus, I am introducing losses in the output beams behind the beam splitter. And this is of course simulated by another small beam splitter and particle loss. In this way, evolution by the beam splitter itself is still unitary, but of course the evolution of the whole system.
But you look at the successor then, yes.
Yes, so this
Yes.
is the side
Yes,
also.
yes.
Then when you,
Yeah.
everything is unitary, but then you reduce it to the subsystem and this
Yes.
is
A
how-
piece of it is not.
Yeah.
That's
I would like to comment on feasibility on this, that this model could be implemented by atoms in optical lattices in the hot insulator phase. They are plans that more occupied hot insulator phase can be created by atomic Bose-Einstein condensates and integrated optics. And these insights are of general relevance because Hong-Ou-Mandel effects have been observed and reported for neutron diffraction, diffraction of X-rays, surface plasmons, atoms, many systems. The outlook for quantum leap is that I hope that it will be find a place in the framework of quantum simulations, allowing to obtain results emerging from long evolution, and not leaving for simulation of processes with dynamic evolution. Hong-Ou-Mandel effect is very important to include in quantum walks because it can be characterized by quantum visibility, and it also effectively imparts nonlinearity, leading to the exchange interaction between photons on beam splitters. This has not been explored. And multimode Hong-Ou-Mandel interference will constitute a setup where various interesting phenomena can be observed, like large-scale interference, Boson sampling, nonlinear phenomena, multi-particle entanglement. Thank you very much.
I'm not sure whether my question is relevant because I am not really very much in your subject, but I have this association. If we have, whenever we have a situation in quantum field theory and quantum mechanics, when we iterate a local Hamiltonian, a local evolution, many times it may be in space, in time, or maybe it's in space, to obtain long distance properties or late scattering amplitudes. There is also always a relevant question of universality classes, which means that certain for the bulk properties or long distance properties of the system, the exact form of the local dynamics is not crucial. Many local Hamiltonians, short distance Hamiltonians produce the same effects. Are people, because you are talking about various models of quantum walk, leading surprisingly to very similar results. Are people considering classification of this mechanism into some universality classes?
There are some attempts. I've seen a paper where they are considering various universality classes because the processes have been found where the spread is faster than ballistic or sub-ballistic but not yet linear. In this way they are. But they are also trying to approach high energy physics. This is not my area of research, but I recently attended a talk where they are trying to indeed simulate quantum neuromodynamics in a very simplified way, because not using the SU3 group but SU2 group, nevertheless some effects they are capable of restoring.
If there are no more questions, we'll thank you.